Hello guys, we're gonna start our fourth lecture on chapter 12. So in this lecture, I want to talk about orthogonal series expansion, and then I'm gonna talk about orthogonal set with respect to one weight function. So in the last lecture, you saw that we can represent any vector in space using three mutually orthogonal vectors. So we have the same for functions. So if we have set of functions phi n x is an infinite orthogonal set of functions on the interval a to b, we can represent any arbitrary function like fx on the interval such that fx is equal to c1 phi 1 plus c2 phi 2 plus up to cn phi nx. And in this case, c1, c2 up to cn, they are all constants, and we have to find these constants. In order to find these constants, so we can have the same process that we had for the vector. So we can say that fx is equal to c1 phi 1x plus c2 phi 2x plus so on up to cn phi nx. If I want to find cn, for example, so what I have to do, I just multiply left and right hand side of the equation by phi n x, and then I take integral from a to b from left and right side of the equation. So here in the right hand side, I have c1 integral from a to b phi 1x phi nx dx plus c2 integral from a to b phi 2x phi nx dx plus up to cn integral from a to b phi nx times phi nx is phi nx squared dx. So I know that the set of function phi nx is orthogonal. As a result, the integral from a to b phi 1 phi n is equal to 0. Integral phi 2 phi n on the range of a to b is equal to 0, and so on. The only thing left is the integral from a to b phi n squared x dx, which is a square of norm of phi n. As a result, I can say that cn is equal to left hand side of the equation, we had the integral from a to b fx phi nx dx, and over the integral from a to b phi n squared x dx, or the integral from a to b fx phi nx dx is inner product of fx and phi nx, and the integral from a to b phi n squared x is normal function phi nx squared. So we could find cn. We said fx it's equal to c1 phi 1x plus c2 phi 2x and so on. If I want to write it in a compact form, so I can say that it's summation of n from 1 to infinity cn phi nx, and we said cn is inner product of fx and phi n divided by magnitude of phi nx squared. In fact, sorry, it's a magnitude of function squared, not it's magnitude of phi nx squared. So this guy is cn times phi nx. n is from 1 to infinity. In fact, we could represent one arbitrary function like fx in terms of functions of one orthogonal set. Now we solve one example to see how this equation works. In this example, we're going to find orthogonal series expansion of fx equal to x on the range of 0 to pi over 2 using following orthogonal set of functions. So we can easily prove that this set of function is orthogonal, and we can find normal function. I can represent this set of function as cosine 2n minus 1 because it's just odd numbers times x, and n can be equal to 1, 2, 3, and so on. So first we have to find normal function, normal cosine 2n minus 1 x. So you can easily find it based on definition of normal function. So normal function squared in this case is equal to pi over 4. So you can easily find it. So now we have fx which is equal to x. We want to write it in terms of orthogonal series. So it's c1 cosine x plus c2 cosine 3x plus so on plus cn cosine 2n minus 1x. And now I want to find cn. Cn is equal to, based on definition, so it's inner product of fx and phi nx divided by magnitude of phi nx squared. In this example, fx is equal to x and phi n is cosine 2n minus 1 x. So I have to find the inner product of these two functions divided by a norm of cosine 2n minus 1 squared. So cosine 2n minus 1 times x. So norm of this function squared. It's equal to inner product of x and cosine 2n minus 1 x. So on the range of 0 to pi over 2 is the integral from 0 to pi over 2 x cosine 2n minus 1 x dx divided by norm of cosine 2n minus 1. So it's equal to, we already found it, it's equal to pi over 4. Here I made a mistake. So here it's cosine 2n minus 1. Now we have to find the integral in numerator. You can easily find this integral. If you find it, you can see that cn, you have to find it by integration by part. If you find it, you can see that it's equal to 2 times 2 minus 2n minus 1 times pi cosine n pi divided by 2n minus 1 squared times pi. So if you find the integration by part in numerator and divided by pi over 4, you will end up with this cn. As a result, c1, if you plug n equal to 1, would be equal to 0.72676. C2, if you plug n equal to 2, so you have minus 0.80. 8138, and C3, for example, it's equal to 0.34907, and so on. So you can find C4, C5, and so on. As a result, we can say that fx, for example, is equal to C1, it's 0.72676, cosine x, fx is equal to what? In this example, it's x. X is equal to this, minus C2, so it's 808138 cosine 3x, plus C3 is 0.0, it's a 0.34907 cosine 5x, and so on. So we could represent fx equal to x using given orthogonal set of functions. In this part, I want to talk about orthogonal set of function with respect to weight function. So a set of real valued function like phi 1x, phi 2x up to phi nx is said to be orthogonal with respect to a weight function wx on an interval of a to b if the integral from a to b wx times phi nx times phi mx is equal to 0. So in this case, n should not be equal to m. So we can use orthogonal set of function with respect to another function to represent any arbitrary function as well. For example, let's assume we have a function, an arbitrary function fx, so I can represent it in terms of orthogonal function with respect to a weight function. So I can say that it's equal to c1 phi 1x plus c2 phi 2x and so on, plus cn phi nx, and in this case the phi n series of phi nx is orthogonal with respect to ws, so it's orthogonal with respect to wx. So now c1, c2 up to cn, they are unknown, so we have to find it. The procedure is exactly the same as we did for orthogonal set of functions. So if you want to find c1, what you have to do, let's say you want to find cn, the general case. So you have to multiply fx by phi nx and wx, and then you have to find the integral from a to b. So you have to do it for both right hand side of equation and left hand side of equation. For right hand side of equation, so we have c1, the integral from a to b, phi 1x, phi nx, wx dx, plus c2 plus c3 and so on, plus cn, the integral from a to b, phi nx times phi nx is phi n squared, wx dx. So you know that because this set of function is orthogonal with respect to weight function, as a result this integral is equal to 0. For c2 again is equal to 0, and we can end up with cn. So cn is equal to the integral from a to b fx phi nx wx dx divided by the integral from a to b phi nx squared wx dx. And so we can represent fx as series of cn times phi nx, and n is from 1 to infinity. So we could represent one arbitrary function like fx using orthogonal set of function with respect to weight function.